Hello everyone. This video is on the Knewton Alta assignment for section 6.4 called Logarithmic Function Graphs. Okay, and in this video I'm going to be going over a preview version of this assignment, so please understand that the questions I see in this video may or may not be the same questions that you see when you work on the assignment yourself. But all the objectives are the same, the structure should be similar, so I'm hoping that watching me do these here helps you in some way when you work on the assignment on your own. Alright, so on your assignment page you should see the title, your mastery bar telling you how far along you've gotten, the objectives. Alright, it looks like there are 4 objectives for this particular assignment. And then underneath the current objective is a question related to that objective. And at the bottom of every question, you should be seeing a feedback button, right, where you can send feedback to Knewton if you wish. You will not have this instructor cheat button. Right, this is for instructors only. But you will have a more instruction button, and you can use this, click on this if you're struggling with a topic, and it'll take you to a page with some further reading or videos to study, and then you'll have questions related to that instruction, and completing those questions is also a way to get through the assignment if you want. Okay, so this first objective I'm looking at is graph logarithmic functions. Alright, so before I get into this specific logarithm with a base of 7, I just want to draw up a little page here on just basic logarithmic functions in general. Right? So your basic or parent, right? Because later in there's one objective in this assignment where we're going to be graphing using transformations. And remember, transformations, you start with some parent function, some basic function, and then perform one transformation at a time. So these are the basic or parent logarithmic functions. And they look like this. F of x or y equals the logarithm base b of x. Now remember, the base b has to be a positive number, and we wouldn't want the base b to be equal to 1 either. Right. And also we saw this in previous videos on logarithms from sections 6.1 through 6.3. The input value has to be positive. We're also going to talk about that. The domain of a logarithmic function, the input, whatever's inside the logarithm, has to be a positive number. If you input 0 or if you input a negative number, it's going to be either undefined or not real. Okay, so this is broken up into 2 cases, kind of like when we looked at the basic exponential functions, y equals b to the x. These logarithmic functions are just the inverses of the exponential functions. So the first case I'm going to look at is if the base is bigger than 1. Well, if that's the case, this is going to happen. So remember, the log base, any base of 1, if the input is 1, the output will be 0. because anything to the 0 power is 1. Remember, a logarithm is equal to an exponent, right? It's the exponent you need to raise the base b to get the input x. And then if b is bigger than 1, it means b on the x-axis would be over here, and the log base b of b would be 1, right? B to the first power is b. And then if b is bigger than 1, 1 over b would be less than 1. And if I plug in 1 over b for x, the output would be -1, right? B to the -1 is 1 over b. And I could keep doing this, plug in b squared and get 2, plug in b cubed and get 3, plug in 1 over b squared, get -2, 1 over b cubed, get -3, and so on. And we get this kind of a graph here. That is it's an increasing function, and I'll write all this information up. Again, the domain is only positive numbers. So the logarithmic function has a vertical asymptote, a vertical asymptote of the y-axis, x equals 0. So yeah, so I'll put all this stuff in, right? Your domain is only positive numbers, right? Everything greater than 0, but not 0 itself. The range is all real numbers, right? It goes down forever, up forever. So the outputs can be any real number. As I mentioned, right, the vertical asymptote. See this, the graph is going to approach the y-axis without actually touching it on the right side here. The vertical asymptote of x equals 0, or the y-axis. And it's an increasing function, right? As the input increases, the output goes up, right? Okay. And you should know all these things about a basic logarithmic function with a base bigger than 1. And then the other case is, well, what if the base was less than 1? But still positive, right? We're not going to consider any bases that aren't positive. So what if the base is between 0 and 1? Right. So it's still going to have the point 1, 0 on it. Right, the log base b of 1 is 0. But now b is between 0 and 1, so when I plug in b, that's going to be here, and the output's going to be 1, right? B to the first is b. And if b is less than 1, the reciprocal, 1 over b, will be greater than 1, and if b to the -1 is 1 over b, the output's going to be -1, like that. And it's like this, basically just flipped across the x-axis. Right. And it's a decreasing function with the y-axis as an asymptote still. So it's got all the same properties here. It's got all these same properties. Same thing there. Domain is all positive numbers. The range is all real numbers. And it has a vertical asymptote of the y-axis, right? X equals 0. Graph is going up forever to the right of the y-axis, but never actually touching the y-axis. But then this is a decreasing function, though. Because as I increase the input, right, the output's going down. Alright, so base bigger than 1, increasing. Base less than 1, decreasing. And domain all positive numbers, range all real numbers, and the y-axis, x equals 0, is a vertical asymptote. So if you know this much, then after you perform some transformations, some of this stuff might change, but at least know this basic stuff so that transformations, you can start from here and work outwards. Right. So the the example we're given, right, in the first question, is graph this. F of x equals the logarithm base 7 of x. And like I say, you can make a table like normal, plot some points, but plug in 1, let's say. The log base 7 of 1, as I mentioned, is 0. No matter what the base is, if you input 1, the output is 0, because 7 to the 0 is 1. And the log base 7 of 7 is 1, right? Since 7 to the first is 7. Right, change it to exponential form and see that it's a true statement. The log base 7 of 1/7 would be -1, right? 7 to the -1 is 1/7, and so on. And I can plug in all sorts of stuff. And this is going to be a graph that looks like the graph I showed you, when the base is bigger than 1. So here's, 7, 1, 1, 0, 7, 1. And then you'd have to go out to 49 to get an output of 2. 7 squared. Log base 7 of 49 would be 2. So I'm not plotting that, but you'd have to go all the way out to 49 on the x-axis to get an output of 2. And then 1/7, right, would have an output of -1, and 1/49 would give me an output of -2. And it's this, very sharply increasing here, and then very slowly increasing out here. But this kind of a function, right, an increasing function with the y-axis as a vertical asymptote. The domain is all positive numbers, the range is all real numbers. Because I know it doesn't look like all real numbers is the range, but this is going up forever, just very, very slowly. And if you want to see an even better picture than this, we can go to that Desmos website. I'm just going to put in y equals log, and then you hit, shift hyphen, and that'll put a subscript. Log base 7 of x, right? And you're seeing basically the same picture I just showed you. See the 1, 0. You got 7, 1 right there. And then 1/7, -1, 1/49, -2. I mean, I can make a table and they'll plot those points. See, negative inputs are bad, right? 0 inputs are bad. I have to put in a positive input. Say at 1/7, say -1, that point's plotted. 1/49, -2, that point's plotted. Now, I know it looks like, and shouldn't have 0, right? Log of 0 is undefined, and I know it looks like it's touching the y-axis, but as you've seen with other asymptotes, if you zoom in close enough, you'll see the graph isn't actually touching the y-axis, right? X can't be 0 here. Okay. Alright, we're back on the assignment though, right? It's a multiple choice. So it doesn't look like that. Well, let me actually wait till the graphs come in, I guess. Oh, it's not even the full graph. It's just asking which of the following shows plotted points which are on the graph of this function. So, again, it wouldn't have any points on the vertical axis, so that's not good. This has 7, -1. We said 7, 1 would be on the graph. So not this. No points, the origin wouldn't be on it. This one here, right? 1, 0, 7, 1. Those points would be on the graph of that function as we saw. And then after you submit an answer, it'll tell you if you're correct or incorrect. And then, at the bottom, give you some sort of answer explanation. Please read through the answer explanations just to make sure you understand why something was correct or why something was incorrect especially, and hopefully you can learn from your mistakes for future questions. Alright, so let's move on. Alright, so here I'm asked to write a logarithmic function from a description. So we're given some logarithmic function and asked to perform transformations and write the final equation, after all the transformations are performed. So, I'm hoping, I'm going to assume here that you remember the Chapter 3 material on function transformations. And I'm just going to perform them. Alright. And we'll take a look, we'll go to Desmos maybe and see the transformations actually occurring and see that they're occurring the correct way that they're described. So here we're given the graph of the function f of x equals the log base 10 of x. Now hopefully you recall too, the logarithm base 10 I can write without base 10, and it's assumed to be base 10. That's called the common logarithm, so I'm going to do that. It's stretched vertically by a factor of 7, so that just means multiply this by 7. Shifted to the right by 5 units. Remember, that's replace x with x minus 5. And shifted down by 4 units, so subtract 4 at the end after everything. Right, I'm going to write that out here. Right, we'll do this on paper. So I'm given f of x, this is the start of it, equals the log of x, log base 10 of x. And then they ask us to first, vertically stretch by a factor of 7. Again, I'm hoping you recall that when you do any sort of vertical transformation, you leave the previous rule the way it is and do something on the outside. So this will be y equals, the log of x, but then the whole thing gets multiplied by 7. Right? So we have 7 times the log of x. Right, and then we're asked to do a horizontal transformation, shift to the right. Right, that's horizontal, 5 units. And again, anytime you do a horizontal transformation, you're just taking the previous rule and just replacing the x's with some expression. To shift to the right 5 units, I'd be replacing x with the quantity x minus 5. Right, that'll shift the previous graph to the right 5 units, and then shifting down 4 units is a vertical transformation. So I leave the previous rule the way it is and do something on the outside, and that'd be just subtracting 4. So our final rule for the function they're describing after all the transformations is this rule here. Y equals, or g, they have g of x equals 7 times the log of x minus 5, and then minus 4 after. And like I said, I'm going to go to Desmos and we'll look at those transformations one step at a time just to see that those things are happening the way they're describing them. So I'm starting with y equals log of x. Remember, this is log base 10. So it's 1, 0. You'd have 10, 1. You'd have 1/10, -1, and so on. And I multiply by 7 times the log of x. And you see how every point, the distance from the x-axis got multiplied by 7. It's probably easiest to see here when you have originally 10, 1 and now it's at 10, 7. Right, and that happened for every point. Alright, so I'm going to turn the first one off. Now we're at this one. Alright, next we were asked to, shift it to the right 5 units. So y equals 7 times the log of, and then instead of x, right, replace x with x minus 5. And you see it's the same picture, same graph, right, just everything shifted to the right 5 units. And then finally move this down 4. I'll just copy and paste it and put a minus 4 after. And now that last graph is the previous line's graph. Everything bumped down 4 units, and there's our final graph. And you see how the asymptote moved also, right? The vertical asymptote for the original function is just the y-axis. But if you ever move to the right or move to the left, like we did here, we moved to the right 5 units. Now it's at x equals 5. Alright, if you put in the line x equals 5, you can see that that's definitely the vertical asymptote for our final graph. Maybe make it a dashed line or something because it doesn't actually belong. Alright, hopefully it's obvious. Yeah, if you ever move your graph to the right or the left, or do some sort of reflection across the y-axis, that may change your domain, and that may change your vertical asymptote. Right. So just keep in mind that kind of stuff. Okay, so I'm entering here g of x equals 7 times the log of x minus 5, and then minus 4 after. And again, this one was fine because it was log base 10. Now, if they had a different base in there, I would have had to put that base in, right? But log base 10 can be written as just log. Okay. Next, we're actually, now we're graphing transformations of logarithmic functions. All right, so once again, now they have a bunch of stuff to move around here. Right? They're saying graph the function below by first selecting the correct reflection, then move the vertical asymptote and the key point. Alright, so I'll show you how we're doing this after I draw it myself. Alright, so I'm going to write this out and talk about how to graph it with transformations, where you start with one of those basic logarithmic functions and do one little transformation at a time to make the equation look like this, like the one they're giving us here. So yeah, so the function we're given, right, is f of x equals the log base 4 of x minus 3 minus 1. Alright, now I've got a couple ways that you can do this stuff. The first way is, with transformations, as they're saying, as they want you to do in the objective. Okay, so we're going to start with the basic version of this, which would just be y equals the logarithm base 4 of x, right? And we know a few points on this. If I plug in 1, I'm going to get 0. If I plug in 4, I'm going to get 1. Alright, and kind of like with exponential functions, because these are just the inverses of exponential functions, you only really need 2 ordered pairs, and of course you should know what the domain is, what the asymptote is, but you really only need 2 ordered pairs, 2 points, to be able to plot the thing. So I got 0, 1, 1, 0, 4, 1, and I know the vertical asymptote is going to be the y-axis. So here's the graph of the original function, something like this, and it's an increasing function like that. There's this graph here. I'll just put the color underneath it. And then we perform one little transformation at a time. Now, one thing I'm noticing is that x is replaced by x minus 3. So that's going to cause a shift to the right 3 units. So you got y equals the log base 4 of x minus 3, and if I shift to the right 3 units, instead of x equals 0 being the vertical asymptote, now it's going to be x equals 3. Right? The asymptote moved. Here's x equals 3. And all these points are moved to the right 3 units. So 1, 0 moves over to 4, 0. 4, 1 moves to the right 3 to 7, 1. Now it looks like it's on that same graph, but it isn't. And I'll do this in a different color. And it's the same picture, just shifted right 3 units. So there's this color, whatever color you're seeing. Alright, so now I'm on this new graph with the vertical asymptote at x equals 3, and then the minus 1 afterwards would shift it down 1 unit. Alright, shift down 1 unit, and we get the function that they asked us for. Right, y equals the log base 4 of x minus 3, and then minus 1 after. So the asymptote would stay where it is. I just move all the points down. Right, so 4, 0 goes to 4, negative 1, and 7, 1 goes to 7, 0. And I'll do this in a different color as well. But it's the same shape, just down 1, and there's our final graph. All right. Now another way you could do this is by stating the domain first, and that'll really help, I feel. So I'm going to put this function up again and go over another, I think, faster way to graph these. So state the domain first. This is just by plotting points, really. Plotting points with asymptote, wherever that vertical asymptote's going to be. So we have, f of x equals the log base 4 of x minus 3, and then minus 1. And remember what I said earlier, whatever's inside the logarithm, so this x minus 3, this has to be positive. And we'll talk more about stating the domain in another objective in this assignment, but I'm going to bring it up now. This has to be positive, this x minus 3. So that means x minus 3, whatever that is, has to be greater than 0, meaning that x has to be greater than 3, and there's your domain. Right, the domain of this function is everything greater than 3, right, from 3 to infinity without including 3. And then you just start plugging in values. So I know where the asymptote's going to be. It's got to be at 3, right, because the rest of the graph is to the right of 3. So there's the vertical asymptote, x equals 3. And then notice the base, right? It's base 4. So plug in values so that you get a power of 4 inside the logarithm. 4 to the first, 4 to the second, 4 to the 0, 4 to the negative 1. So obviously if I plug in 4, for x, I'm going to get the log of 1, which is 0, and then minus 1 will be negative 1. Right? So 4, negative 1 is on this graph. I plot that point. And then another power of 4 would be 4. Right? If I plug in 7 for x, if I plug in 7 for x, 7 minus 3 is 4, and the log base 4 of 4 is 1, and then 1 minus 1 is 0. You get 7, 0. And again, if you know where the asymptote is, and you know a couple points, you should be able to draw a rough sketch of the graph. It's some function that looks like this, going through these points, approaching that asymptote, something like that. All right, and that's kind of like the graph I had on the previous page after all the transformations. All right. Now, to be honest, I actually prefer graphing logarithmic functions this way. I think it's easier. I think it's quicker, but yeah, sure, you don't understand the underlying transformations, and if you're a student of this and you're first learning, you should probably go through the transformations just to understand where the thing's moving from. Alright, now back to the assignment. We have to move some stuff around. First off, let's see, move this box here. There, it needs to be like an increasing function. And I think this will reflect it. Yeah, I don't need that. It's not going to be on that side of the asymptote. The graph's on the right side of the asymptote and increasing. So the graph looks like this. And we move the asymptote over to 3, and move that key point, we're not at 4, 0. Remember the 4, 0 moved down to 4, negative 1. And there we go. And just make sure that that's 4, negative 1. Asymptotes at x equals 3. Cool. Graph's increasing. This is the one we want. This looks like what we had drawn on my paper. Wonderful. Okay, moving on. Alright, so this is just identify the domain of a logarithmic function, which I just did on the previous example. Alright, all you have to do is remember that the number inside the parentheses after the logarithm symbol, right, the number inside the logarithmic function has to be positive. It can't be 0. It can't be negative. Alright, so this function here, we have the natural log. Remember, this ln means log base e. We have the natural log of 3x plus 1. And they're having us put the result in interval notation. Notice the parentheses around that. Yeah, so g of x equals, the natural log base e of 3x plus 1. And just like I said on the previous example, when you're stating the domain, you're trying to figure out, what can I plug in for x? You have to remember that the number inside the logarithm has to be positive. Right, this has to be a positive number in order for you to get a real number output. And so you set up that inequality, right? This expression inside the logarithm, 3x plus 1, has to be positive, has to be greater than 0. And then we solve this for x, subtract 1, divide by 3. X is greater than negative 1/3. Alright, and if you were graphing this, that means the vertical asymptote would be at x equals negative 1/3. But the domain here is all we're asked to state. It's everything from negative 1/3 to infinity, right? But not including those, right? The parentheses on those. But every value greater than negative 1/3 can be plugged in for x here, and you'll get some output. And this is what they want, right, in interval notation. So they already have the parentheses in for me. I just need to put the values in between. So negative 1/3, comma, and then infinity. Great. Alright. So those should be quick, the identifying the domain ones. Alright, so here graph the function of f of x equals the log base half of x. And it says here you can only graph integer points, so you can't graph things with fraction values, unfortunately. There is one point that can be moved above and below the x-axis as needed. Do not move either point off the graph. Alright, so we got a couple points to move here. Alright, so I'm just going to go to paper first, show you. And now this is a very basic logarithmic function. Just the log base a half of x. Like I said, every single basic log function is going to have the point 1, 0 on it. So I'll plot that one at least. And then 1/2, 1, right? 1/2 to the first power is a half, right? And then 2 is the reciprocal of a half. So if I plugged in 2 here, I'd get negative 1, right? 1/2 to the negative 1 would be 2. And it's one of these decreasing functions, right, with the y-axis as a vertical asymptote, right? Something like this. If you want to go to Desmos, make a better picture, please do. But yeah, so the only ones we can plot, though, they told us, are 1, 0, and 2, negative 1, maybe 4, negative 2, right? Powers of 2 will help me here. And that's what I'll do. I'm going to plug 1, 0 is already there. I'm just moving the other point to 2, negative 1. And there, and it's got the vertical asymptote at the y-axis and looks exactly like it should. Great. Alright, next. Alright, so another one of those where we're given a function and asked to do some transformations. Alright, so these I'm just gonna type it out as I go. So we start off with the log base 5 of x, right? Don't forget the base 5 there, or whatever base is there. Unless it's base 10, you don't have to write base 10 if you don't want to. Stretched vertically by a factor of 2. So that means I take this and multiply it by 2, so I got 2 times the log base 5 of x. Reflected over the x-axis, so that's just multiplying everything by, the whole previous rule by -1, so now it's -2 times the log base 5 of x. Reflected over the y-axis means replace x with -x, so now I have this, -2 times the log base 5 of -x, and then finally shifted up by 1 unit, so after everything, the previous rule stays the way it is, and then I throw a +1 on it, and that'll move everything up 1. Yeah, so like I said, I'm assuming you remember the function transformations. These should be pretty easy if you remember how to perform those. Great. Okay. Back to this, identify the domain of a logarithmic function. So again, pretty simple stuff, I feel. X minus 6, right? Whatever the expression inside the logarithm is, that has to be positive. So x minus 6 has to be greater than 0. You add 6 to both sides, x has to be greater than 6. So the values you can plug in are from 6 to infinity. So I have the parentheses already, they have them for me. The intervals is from 6 to infinity. This one's graphing transformations. Alright, so like I said, I guess we could just do what this does here. Alright, this is the log base 5 of x plus 1. The log base, right now they have graphed the log base 5 of x. You see you got 1, 0, you got 5, 1, the vertical asymptotes at the y-axis. So this one here, if I multiply by -1, that reflects it across the x-axis like that. And then replace x with x plus 1 moves everything left 1. So now the asymptote is at -1 instead of +1. And it should have the point 0, 0 on it, and you can test that out. And the point 4, -1 would be on there, and you can do all that stuff yourself. That shouldn't be so bad. Alright, so here's another one with a basic logarithmic function. It's the log base 1/8 of x. So that's kind of 1, 0, as this does already, and then 8, -1 is the other point we can plot here, because you can only plot points without fraction coordinates, right? So you'd have 1/8, 1, 8, -1, right? Just like the log base half earlier, but it's base 1/8, right? So powers of 8 would be a good good inputs here. And it's got decreasing like a logarithm with a base less than 1 should be a basic logarithm. Y-axis is the vertical asymptote. Looks good. Okay. Alright, so one more of these. Log base 1/6 it looks like. So basically just like the 1/8 one, or the 1/2 one earlier. It's got to be decreasing. It's going to have the point 0, 1 on it, or 1, 0. I keep saying 0, 1. I apologize. It's got the point 1, 0 on it, and it's log base 1/6. So 1/6, 1, or 6, -1. That would be the other point that I need to apply here. And there's the graph that they're looking for. Alright, cool. So that objective's done. Shouldn't be too bad if you know your basic logarithm functions. Alright, and again, the domain thing, pretty simple. You just have to set this greater than 0 and solve. Now this one's a quadratic, so it's a little trickier. So let me do this on paper this time. Now I hope you recall how to solve a quadratic inequality. This is what we're going to have to do here. So I have g of x equals the log of 16x minus x squared. And once again, we're asked to state the domain. This expression inside the logarithm, 16x minus x squared, this must be positive. Right. Now, again, how do you solve a quadratic inequality? There were a few ways. You could look at the graph of this quadratic function and see for what values of x is the output positive. Or you could try to find, factor this thing, which it is. It's factorable, right? They pull x out, then you have 16 minus x greater than 0, and then you made a little number line with possible values of x, and then up here, values of 16x minus x squared. And this expression was equal to 0 at x equals 0. Right, so that wasn't a solution. So I have an open point above here because we're looking for values that make this greater than 0, not equal to 0. That's why I got an open point above 0. And 16 would also make this left side 0, which is not greater than 0, right? So open point above that. And then each of these critical values, right, 0 and 16, I plug in values around those and see if we get solutions or not. So over here to the left of 0, I plug in -1. This would be -1 times 17. That'd be negative. Is that greater than 0? No. The numbers in between 0 and 16 will work. Right, say I plug in 1 or 2 or 3 or 15 or pi or whatever, you're going to have a positive number on the left, which is greater than 0. And then numbers over here, like 17, 18, 19, when you plug them in, you get negative numbers on the left, which aren't greater than 0. So the only solutions are these numbers here from 0 to 16. Right, here are the solutions of this equation, of this inequality, and therefore those are in the domain of this logarithmic function. Right, you can only plug in numbers between 0 and 16 because only these numbers will give me a number inside the logarithm that's positive. So I'm hoping you remember a little bit about how to solve higher degree inequalities. Alright, so back here, now they asked us for interval notation. Here they didn't give us the parentheses, so I need them myself, 0, 16. Put parentheses around those. And there we go. Okay. And again, read through the answer explanations. Maybe that'll help in the future. Alright, so one more of these where, what's the domain? So I'll write this final one out. So we have g of x equals the log base 2 of 7 minus x. And once again, it doesn't matter what the base is on the logarithm. Just remember that whatever's inside the logarithm needs to be positive. So 7 minus x needs to be greater than 0. And I solve this inequality. Now this is another linear inequality, so it's a lot easier. I just add x to both sides. So 7 needs to be greater than x, or if I switch sides, I got to flip the symbol. X needs to be less than 7. So we're talking from negative infinity up to 7 is the domain of this function. And if you were to graph it, the x equals 7 would be the vertical asymptote, and the rest of the graph would be to the left, right, where the x values are less than 7. Now they gave us the parentheses already, so we're going from negative infinity, comma 7. Right? Parentheses are already there. Great. Okay. Graphing transformations. So again, there isn't much to do here. Now they already gave us, they're starting out with those parent functions. This is the graph of the log base 3 of just x. So you got 1, 0, you got 3, 1. Y-axis is the vertical asymptote. So multiplying on the outside by negative 1 reflects you across the x-axis. So let's move that thing down 1. There's a reflection across the x-axis. And then I would have to replace x with x plus 3, which would move everything left 3. So I'm moving the asymptote left 3, and there you go. And you can double check that negative 2, 0 would be on this, and 0, negative 1 would be on this. You can double check that stuff if you wish. Great. Alright, looks like I got one more of these. Where again they're starting off with the basic log base 3 of x. This is the graph here of the log base 3 of x. And replacing x with x plus 3 would move it left 3, so I move the asymptote left 3. And then having the minus 1 after everything just moves it down 1, so I take my key point here, move it down 1, and there's the graph. Alright. Wonderful. Alright, so that stuff's done. And again, you can do that stuff by hand, use Desmos to help you, calculator, whatever. Alright, and then the last couple problems here, I just got to, again, start with some basic log function and perform transformations, which I'm just going to type out here one at a time. Alright, so we're starting off with y equals, the log base 4 of x, and that's the starting point, the parent function. Once again, we're stretching vertically by some factor. Means multiply by that factor, and that should be a number bigger than 1 if you're stretching vertically. And if you're compressing vertically, you're multiplying by a number less than 1. Reflected over the y-axis means replace x with negative x. Right? And then shift up by 3, so after everything I put a plus 3. And there we go. The graph of this will be the graph of that original with all these transformations performed. I should have just one more of these. And again, if you know all your transformations from chapter 3, this should be simple. So I'm starting off with the log base 7 of x and doing some stuff. Alright, so again, I write this out in the box here. Log base 7 of x. And it's stretched vertically by a factor of 4. So I'm multiplying the outside by 4. 4 times the log base 7 of x. Shifted to the left by 5 units. So x is replaced by x plus 5. Would move it left 5. So now I have 4 times the log base 7 of x plus 5. And then shifted down by 3, so on the outside, minus 3. And there we go. Great. Alright, and that should be it for this preview version of this assignment. So, like I said at the top of the video, right, the questions I saw here may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, the structure is similar. So I'm hoping that watching me do these here helps you in some way when you're working on the assignment yourself. And thank you very much for watching.